Perfect. I think we can start now. Okay, so let me share my screen. Okay, good. Now you should see my website. And keep in mind that when I share the screen, it's difficult for me to see the chat. So if anything goes wrong, please just turn the mic on. And 1 second, because people are still coming in. Okay, good. Okay, so let me see if I can adopt a better setting. 1 second, only 1 second, because let's see if I can also look at the chat. Yeah, okay, now you should see my website, and I think in principle I could be able to see the chat. Let me open it. Okay. Okay, I think this is better. Okay, let's go to our web page, and here are the links. So you may remember that we got here to the Earth system. Let me just increase the font so you can see it better. So let's click on the Earth system here. Good. And we got somewhere down is in the bottom of the web page, the link. And let me just open it. Okay, good. We can open it. Perfect. Let's put it in presentation mode. And let me, I think we got here, tipping point of the socioeconomic system. Just 1 second, I go back to the web page and get here. Good, same point. Very good. Let me just 1 second. I think this is LibreOffice. Okay, let's try to use LibreOffice. It's not really PowerPoint, that I'm using. It's LibreOffice, but I think it should work. Okay, so we closed the last lecture by talking about tipping points, which I defined as state of the system, limiting states of the system, from which we can get to more than one equation. So if we are in an equilibrium situation, then at a certain point, we may reach a state, a tipping point, where even a small perturbation of the system can bring me to another equilibrium situation. And I made the example of the forest and the brushes. So these tipping points are typical of the Earth system. You may remember the previous slide here, where we introduced a lot of tipping elements. So it means parts of the Earth system which can give rise to tipping point. And we mentioned the dieback of the Amazonas, the melt of the Greenland ice sheet, and many others, okay? And then we said even in the societal system, we may have more than one equilibrium state. And for some perturbations, the societal system may pass from an equilibrium state to another equilibrium state. The typical case is the elections. And 1 second, because I have continuously people getting in, and I need to admit them. Okay, good. So one typical example is the elections. You are in an equilibrium state where a party has the majority in the government, which is a cascade of implications. And then your election is an equilibrium state where another party takes the majority, and therefore there are societal changes which supposedly bring the socioeconomic system to another equilibrium state, which is different. In some cases, you may easily go back to the previous equilibrium state, and in the socioeconomic systems in general, it's easier to pass from an equilibrium state to another one, with respect to the Earth system, where in some cases it may be very difficult to go back to a previous equilibrium state. So you understand that getting a knowledge of these tipping points is complex and at the same time much important. Now we are in the phase of our discussion when we try to get an understanding, a qualitative understanding, a broad understanding of how the systems which we are interested in work. And in a subsequent phase, we will need to translate this understanding into predictive tools that can allow me to make a prediction. For instance, if I got an understanding of a tipping point, a broad view of a tipping point, and if I were able to translate this broad view into a predictive tool, I eventually will be able to make predictions to avoid, for instance, to cross the tipping point. This is our target. In climate change adaptation, we need to get an understanding of the climate system, and we start with a broad view, and then the next task is to set up a predictive tool in order to understand what will be the effect of strategies to adaptation. And the same can be applied to mitigation. It's the same thing. And we are talking of both the Earth system and the societal system, because in adaptation, it's the societal system that has to adapt to climate change. This is the purpose of these slides that should bring us to gain a broad understanding of what we're talking about. Okay, so now we have to make the next step, and the next step is the predictive tool. We should be able to elaborate a predictive tool. So let's try to move towards the next step, and let me see if the next slide is already here. Yes. So what are these predictive tools? We call them in general models which allow us to make predictions. So many times we listen to the media saying climate models say this, this, and this, or societal models, economic models, they say that the effect of a new form of taxation will decrease the public debt of a certain amount. And therefore, models are the tools we are looking at. And the models may have different settings. We are in the context of science. In the context of science, typically models are expressed in the form of mathematical tools. They use equations in order to get a quantitative description of the process. Mathematical models are not the only possible solution. They are not the only category of models. We may have also predictive models that are based on heuristic approaches. Heuristic means that basing on my knowledge, without using any equation, I make a prediction. So for instance, I may look out of the window and say, it looks like tomorrow is raining, or I may look at the meteorological predictions, and after looking at these predictions, I may conclude, without using a mathematical model, tomorrow it will rain. In this case of the meteorological prediction, actually, I based my intuition on a mathematical model, which is developed by others, the Meteo Service, and presented by others, the Meteo Service. But at the end, my final decision, my final prediction is based on my personal elaboration of this kind of information. So I'm using the models only indirectly. So this reasoning is to say that when we talk of models, we may refer to several categories. And in science, we are mainly interested in mathematical models, because in science, we are talking about nature. We are talking of processes that are governed in most of the cases, in many of the cases, by the laws of physics, or in other cases by the laws of chemistry and biology. But in any case, these laws can be translated into mathematical models. And when it's possible, it is advisable. It is advisable because the mathematical model is objective, is quantitative, and it's more easily testable. When it's not possible to elaborate a prediction on the basis of the math of mathematical equations, then we can resort to other solutions, more, let's say, heuristic. Heuristic means ad hoc, means something that we elaborate basing on our reasoning rather than basing on a mathematical equation. You shouldn't be afraid if you listen to the term mathematical models. Mathematical models are not necessarily complex, are not necessarily complicated. Some models are very, very easy. We will see that we will see some examples of models that are very easy. For instance, a very simple mathematical model is the persistent model, which assumes that the condition of tomorrow will be the same as the condition of today. And so I look out of the window and I see that it's raining, and a very simple model is to assume through a mathematical equation, an equality, to assume that the conditions tomorrow will be the same as today. So this is a very trivial example of a very simple model, so you shouldn't be afraid. And there is a second reason why you shouldn't be afraid by mathematical models. Usually we are afraid of mathematical models because we are afraid of mathematics, because mathematics is not easy to understand and it's not easy to remember, especially. But today we have computational tools which are unprecedented. If you go back even 15 years ago, the computational tools were much lower. If you go back 30 years ago, we had no computational tools. So today we have these computational tools that allow us to simplify mathematical computation. We may use also softwares that are already prepared. So we can really simplify things. So you shouldn't be afraid of these models. One thing that you should be afraid of is that the model can be wrong, for sure. So the model can be wrong. I would say it's wrong for sure. It's there are few examples of models of the Earth system that are very rigorously precise. I would say that probably none. If you look at a very strict definition of rigorous, there is always some uncertainty. And in some cases, the models can be plain wrong. So this is what you should be concerned of. You use models, you have to make sure that you are aware of the uncertainty. Because, as I said, if an engineer, if a scientist, if a policymaker is aware of the uncertainties, it's no problem. The problems come when we get into uncertainty and we don't realize it. This is a huge problem. If you are responsible for a decision, if you're a policymaker, if you are an engineer, if you are a scientist, and you don't realize the uncertainty associated to your moves, to your decisions, this is a potentially huge problem. So you should be indeed afraid of uncertainty, not mathematics. And in particular, when modeling the Earth system. And what is, I anticipate, what is a basic requirement in order to deal with uncertainty? You have to understand what the model does. You have to understand the theory. This is another possible problem of modern computational means. You are now able today to run models without knowing anything of what they do. You get a software and you run a model. This is potentially dangerous because the software may be affected by bugs, may be wrong, the model may be wrong, and if you don't understand what a model does, then you are really exposed to the negative implications of uncertainty. So this is why we study the theory, because before applying a model, you need to know the theory. You need to know what you're doing. And this is something you should be afraid of, okay? Okay, so mathematical models, they are essential to cope with the impact of climate change and to cope with climate change in general. We use climate models, as I said. And climate models actually allow us, as I said, to make prediction. And we go back to the essential role of predictions. And to make prediction under change is difficult. And This is why we also use models. Remember that models are not the only tool that you need. You also need data. You also need data. And unfortunately, as we said, we don't have a huge amount of data in climate modeling and in hydrological modeling in general. I say hydrology because it's the science of the water cycle, and you know that it's important. So for our purpose, for the purpose of modeling, we have today available several different solutions to model the Earth system, several different models. So it's one other basic requirements to apply a model is to know the possible solutions. Unfortunately, sometimes we don't know all the possible solutions, and we get into a risky situation because we may take the first model that comes to hand, or we may take the model that we know better. We may take the model that is easier to apply. These choices entail a potential risk. Ideally, we should know all the possible solutions and select the best one basing on our requirements, basing on the context, basing on the problem, basing on the uncertainty, because each model is associated to uncertainty. Today, we are in a lucky situation. There are possible modeling solutions. The downside is that it's impossible to know all of them. When we talk about models of the Earth system, if I refer to my field, hydrology, I don't know all the models because it's impossible. In this situation, the engineer and the scientist need to take the safest solution, which is to try to know more models, as many models as possible. So you need to read the literature, you need to stay informed, you need to read, to study, to continuously study. And an help that you may get is classification. When you have to explore a complex environment, or let's say a multivariate, a diverse environment, an environment that is multifaceted, which several possible alternatives, classification helps a lot. And this is why I also insist on classification of solutions. So we may therefore introduce a first classification of models. And let's distinguish between, first of all, what you see on the screen, process-based versus empirical models. So let me anticipate one thing. The models, we are talking about mathematical models, they are expressed by a set of equations. Typically, one basic requirement that you have is to first identify the unknowns. The unknowns are typically your variables that are necessary for design. Let me make an example. If you have to design a bridge, okay, crossing a river under climate change, you need to know several design variables. But from my point of view, the point of view of an hydrologist, I need to know for sure the flood flow of the river, the flood level. I need to know the level that the water in the river may reach, and my bridge should be placed above that level. Okay, so the design variable is the water level, which is also called river stage. Okay, so this is an unknown. In general, you need at least one equation per unknown. If you have one unknown, at least you need one equation. Unfortunately, you may need more equations because in order to describe your predictive, your variable to be predicted, often you have to introduce additional variables that describe the state of the system. So for instance, for the river stage, usually you can express it as a function of the water storage into the upstream part of the river. Because if the river, this is something that you can grasp, you can understand. If the river is able to store a lot of water, then upstream, then you have less water downstream. So the river stage is lower. I say it again. If upstream the bridge, the river can store a lot of water, a huge volume of water, you get less water downstream, you get less water under the bridge, and therefore the water level will be lower. So you understand that the storage upstream the river is something that has an effect on your variable to be predicted. And therefore you have also to model the storage. The storage is changing in time, like the water level into the river. And therefore you need also to describe the storage. And the storage is an additional unknown because it depends on several things. So you have to model it. So it is not a variable that is necessary to your prediction, but it's a variable that is necessary to make your prediction. And we call these variables, which are internal variables of the system, internal variables of the model, we call them state variables, because they describe the state of the system. So you may need to describe additional variables, additional unknowns, and therefore you need additional equations. It is very trivial, it is very simple. You have a set of equations that describe the variables, the unknown variables, including the variable to be predicted, the river stage in this case. These equations may have different forms. And of course, we need to identify this equation. This is a nice task of the modeler. The modeler knows that has to describe, in this case, the river stage and the river storage. So the modeler thinks, what kind of equation can I use? And I may refer, in this case, we are talking about movement of fluid. The case of the river, the bridge, is movement of fluid. And it's movement of a body, in this case, a fluid. And what are the equations that I may use? If I am a scientist, I know that the movement of bodies is described by physics. And therefore, I could refer to the equations of physics. In this case, what my mind does is, basing on my understanding of the process of the system, with system, I mean the river and the upstream part of the river, everything that in this case I have to physically describe. So basing on my knowledge of the system and basing on my knowledge of the evolution of the system, we call this evolution of the system a process. Evolution in time and evolution in space is a process, okay? So basing on my knowledge of the system and the process, I say, okay, I can use the laws of physics. For instance, I can use the first Newton law, the law of motion. Okay, so and in this case, I refer to the intimate nature, to the intimate physics of the system. And we call this approach a process-based approach, or it's not written here, a physically based approach. Physically based is a term that only refers to physics. Process-based is more comprehensive, refers to the nature, the intimate nature of the process, okay? And therefore, process-based models have a theoretical foundation. In this case, the foundation is in the theory of physics. Do you follow me so far? Do you have any question? Here, now, some of the things that I'm mentioning, like, for instance, the term physically based, is not in this slide. You will find something in the web page, and keep in mind that usually after my lectures, I may update the web page. So maybe that there is something that you don't find now and you will find it later. This is quite usual for me, because basing also on the input from students, basing on my understanding of what the student would like to discuss, I may introduce new considerations. I had a good feeling with you during the first two lectures, so I feel that I can introduce something more with respect to last year. Maybe that I am wrong. So I, again, don't hesitate to let me know if there is something that you are not getting fully, okay? So what is the counterpart of process-based models? Let me look at the chat. Nothing there, okay. So what is the counterpart of process-based models? The counterpart is what I'm mentioning here with the term empirical models. Empirical models are not based on my understanding. Empirical models are a simple input-output relationship. And the structure of this relationship has nothing to do with the process. It is just empirical, okay? And this is something that is very often, very frequently done in Earth system modeling. So we write down mathematical equations that are describing the process in the best way, in a ad hoc way, so in a user-friendly way, empirical way, and there is, once again, no, in this case, physical foundation. Of course, given that the process that you have to describe is the same, if you write two models, one that is process-based, physically based, and the second one is empirical, the result that you will get at the end, more or less, hopefully, is the same. And therefore, the two models will become quite similar. We expect similarity. But the starting point is completely different. With process-based models, I start from my knowledge of the theory. With empirical models, I start from a practical solution that, in my opinion, gives the best result. So I start from empirism, not from theory. What is preferable? It depends. It depends. Okay, it depends because typically the level of information that you require to run an empirical model is different with respect to the information that you require to run a process-based model. And also uncertainty may be different. So it is your problem, your context that leads you to the selection of the best model, your experience, and maybe also your preference. So two different scientists may select two different models. Hopefully they will come to very similar conclusions, but model selection is at the end of the story a subjective choice. Another classification, which has nothing to do with the previous one. Another classification, let me introduce it by starting from the second category listed on this slide. Deterministic models. Deterministic models are mathematical models, and they have this distinguishing feature. It's a one-to-one relationship from input to output. Input is our data, our information. For the case of the river, maybe rainfall. Okay. Output is river stage in the example that I mentioned to you. Okay. So the relationship between rainfall and river stage is one-to-one. It means that for a given input, you get only one output. And it's the same one. If you rerun the model, you get always the same output. Okay. This is a deterministic model. It is what you are expecting from a mathematical relationship, by the way. Okay. And then another category, which is the counterpart of deterministic, is a model that if you run it again, you get a different output. For the same input, you get a different output. Okay. And these are models that have a random component. It's clear. If for the same input, same model, you get the output that anytime is different, it means that there is a random component. There is a component of randomness, of causality. And let me give an example of a process with a random component. Again, the river flow. There is a micro open. Please try to switch it off. Again, the river and the bridge. And once again, there is a micro open. Please turn it off. Okay, check your micro, please. Okay. Again, the river. I describe a relationship between rainfall and and the river stage, rainfall is measured. And when I measure rainfall, there is some uncertainty in it. It means that if I give the same input data in terms of rainfall, like 100, I know as a modeler that it's not always 100. 100 is the measured one, but it could be 99 or 101. So I allow the model to perturbate my input data, to introduce an uncertainty. So one time the model is run with rainfall 99, the next time is run with the rainfall 100, and the next time is run with the rainfall 101. I introduce a random component in the model. What is the purpose? The purpose is that, just 1 second, because I think I need to close the micro myself because I see that there is somebody with the micro open. Just 1 second. Okay, Paiman Tari Moradi, your micro is open, okay? I'm closing it, okay? Please try to listen to me. Okay, so what is the purpose of allowing this random component? The purpose is that I know that even if I measure rainfall 100, this measurement is not precise. I know that even if I have an input, a fixed input, actually the input may be varying within a range. And therefore, if rainfall is 100, I want to see what happens for rainfall 99, rainfall 100, and rainfall 101. And therefore, I will get a set of output, and I will check the effect of my prediction by referring to the whole set, not only one. So you understand that this is an opportunity. Provided I can quantify the range of uncertainty, it's an opportunity. The stochastic model gives to me an opportunity this causal model gives to me an opportunity to assess what is the effect of uncertainty in the rainfall, in the input data. The same uncertainty could be related to other causes, not only input data. There might be uncertainty in the boundary conditions. We will see what are the boundary conditions, but let's say in the context, okay, in the context of, for instance, the geometry of the river, my knowledge of the river. There might be other sources of uncertainty. Stochastic models, and let me introduce this term right now. These models that allow randomness, they have the great advantage of allowing me to deal with uncertainty, to estimate the effect of uncertainty. You understand that it's a different situation with respect to the deterministic model. The deterministic model doesn't account for uncertainty. It's one input, one output. The causal model takes several inputs, generates several outputs, okay? Good. Now, what is the name for these causal models, for these models incorporating uncertainty? You can use different terms. You can say that they are causal models. You can say that they are random models with a random component. I like to use the term stochastic model because stochastic is a more comprehensive term. Let's use it as a synonym without getting into boring details. As a synonym of random model, causal model, okay? Let's say that what is the reason, the specificity of the term stochastic? Stochastic refers to modeling in time usually, or modeling in space. And so this is why it's more comprehensive, but I think these details are not our interest now. What is interesting for us to know is are the different categories which we can use. So you understand that we are getting into a fascinating field, a field that is purely scientific, and my treatment in view of the fact that you are not all engineers, and there are also, and this is a fortune, there are some of you that are social science students, and I think this is, we are lucky because a diverse composition of the of our group, it's an added value. And so my treatment will try to be not purely mathematical. Of course, there will be some mathematical development, and you already know that this mathematical development, and I will say this explicitly, it's not for all of you, meaning that I invite all of you to follow, but your exam, for some of you who are students, not engineering students, your exam will not include these mathematical developments. And this is something that please don't hesitate to clarify with me. Okay, if you have some doubt, if you are a non-engineering student and you are in doubt whether or not a particular topic maybe may get into your quiz, into your exam, please ask me if you are in doubt, okay? Because I want to be very clear. But as I said, we are getting into an exciting field because I mean, it's related to our capability to understand the system and model it, to make predictions, what the future will be. This is really very exciting. And in order to do that, we have to use our experience, but also we have to use the theory of physics, of mathematics, because it's the combination of theory and expertise that allows you to get the best result. Okay, let's move forward. So mathematical models. Here you can see a nice sketch. I say nice because I made it. Okay, this is my creation. I put also it on Wikimedia Commons. Wikimedia Commons, let me just, so we make a short break. Wikimedia Commons, what is Wikimedia Commons? So let's go to Google Wikimedia Commons. Wikimedia Commons is a collection of pictures and video which are public domain. I use Wikimedia Commons a lot for my lecture, for my web pages, my lecture notes, because it is indeed comprehensive and useful. So if you type here flood, for instance, in the search box, you get several pictures of floods, and in this case it's very generic because I just put the term flood and I didn't put any location. You can recognize here some of the figures that I use in my web pages, like this one and the Katrina New Orleans. You remember that you saw it in one of the slides that I presented to you, and then here you get a lot of other figures. And if you look for flood Europe or flood Italy, let's say, related to Italy, what is interesting to do is flood Romania. It was just last May, and there are very nice also pictures of the flood that took place in the Romagna region, and some of them you can find in my web pages, and I think the nicest one is, let's go down, by the plane are very nice. I just browse them quickly, and you can reuse these figures. The only thing that you need to do is always check the permission, but what you can find can be used. You just have to cite the source, and I just want to show you what I do usually. For instance, I reuse this one, so you get the figure. If you click on download, you see there is the attribution, European Commission Dati Bando attribution via Wikimedia Commons. What you have to do if you use the picture is to copy this attribution. You make a cut and paste, and you attribute it. Okay. And you can find also videos, not many. There are other public repositories, but Wikimedia, it's easy to use, and it's quite well populated. And one other thing, an interesting thing that you could search for is drought for river 2022. This is, you know, this is nice. This is the progress of the drought from a green condition to a more brown condition. Okay, and here is another interest taken into account. We had this big drop. Okay, so said I put this figure. It's a models, and here you see the risk is 1 also, and here is an example of transformation of rainfall to river flow. This is a typical application. Rainfall runoff modeling allows to make predictions of floods and water resources management in general. So you get a mathematical model that you feed with rainfall data, and you get as output river flow. And there are several state variables that you need to describe, and therefore more than one equation typically. There are models that use only one equation, but typically they use more than one. Let me check the time. Okay, it's still very early. So the stochastic model is many-to-many. It means many inputs and many outputs. You see a pictorial description of what I said. So you see that rainfall is not only one. Now rainfall is within a gray band. Look at the bottom left graph. I put my mouse over it. I hope that you can see it. So in this graph, you see that rainfall now is defined within a gray band. So you get many rainfall, and many-to-many, you see the arrow, many-to-many. It means that many rainfall lead to many river flow. And you see, in fact, that the river flow is described by a gray band, okay? And you see that there is uncertainty assessment through this operation. So precisely what I said, this figure can be found in my lecture notes. And here there is an addition, a stochastic model, but physically based. So it's a combination. This is a demonstration that categories can be, different categories can be cross each other. If we go back to the previous slide, you may remember that we had process-based or physically based models and empirical models, one subdivision in two categories. Another subdivision was that of stochastic versus deterministic. And they can cross each other. You may have a stochastic model that is physically based or empirical. You may have a deterministic model that can be physically based or empirical. You may have any possible combination between these two categories, okay? And so this is, as I said, a pictorial of what I just introduced. Okay, now uncertainty. Uncertainty, I think we already said a lot of it. And so there is not much to say, much more to say. And uncertainty through stochastic models can be dealt with directly. And I want to stress once again, because I'm not sure I already stressed it with you, the role of ethics. So when you make a project, when you develop a project, be careful about the theory. You have to be aware of the theory. You have to be careful of model selection. And in taking these decisions, keep in mind that there are ethical codes for the profession of scientist, researcher, for the profession of lawyer, for the profession of engineers. And it's important that you know these ethical codes, because I mean, ethics, it's not only related to avoiding something that is illegal. Ethics also provide recommendations on what are the most advisable procedures. For instance, one recommendation of ethics is diversity. When you form a team, it's important that you make sure, if it's possible, that there is diversity. And diversity means several things: diversity of gender, diversity of opinions, diversity of geographical origin, etc. So this is one of the pillars of ethics today. And you may think something like, this is not related to engineering, this is not related to diversity, it has nothing to do with designing a bridge. Actually, this is not true. And it has been proven that it's not true. For instance, since 1992, from the Dublin Conference, it has been recognized in water resources management the essential role of women, because women are bring a different perspective. And so when I tell students, some students contact me because they want to work abroad for preparing the thesis. And yesterday I had a conversation with the students, and they said, I suggest you this location because there is a very stimulating, diversity is stimulating. And if you are stimulated, you work better. And there is also to say that today your profession as an engineer, as a lawyer, as a social scientist, as a researcher, as a scientist, involves communication. And communication means that you have to interact with people. And people is much easier if you are a person embracing diversity. Otherwise, it's much difficult to interact with people. And there are several examples that can be made in politics, in whatever field, where we see that the lack of diversity is undermining communication. So beware of the ethics of your profession. And in particular, when dealing with uncertainty, there are several tough decisions to be made. Should I communicate uncertainty? Should I keep it for me? Because, uncertainty means, in a way, to undermine the confidence of the public in what you're doing. So there are relevant questions related to uncertainty. And in order to, to get oriented, I recommend you to refer to ethics. Ethics of engineering, if you look on Google, there are several recommendations and there are several ethical codes. And I am sure that if you Google it and you look at the recommendation, there is something that looks new to you, like, I didn't think of that before. So just beware. And today in science, there is a lot of emphasis on ethics. When I talk about diversity, keep in mind that today it's also important to get a diversity of opinions, diversity of interpretations. Usually when one talks about diversity, people think of diversity of gender, diversity of ethnics, etc. And diversity of opinions is sometimes dismissed because we have a natural inclination to go with the majority, or to be very convinced of our opinion to the point that we dismiss the opinion of minorities. And this is something that should be really avoided. And all opinions, irrespective of the size of the group bringing them forward, should be respected. The only requirement is that they are expressed in an ethically correct way. If an opinion is expressed in an ethically correct way, an opinion shouldn't be dismissed. And this is a bit sensitive today, because today there is especially for some issues related to science and engineering, there is the emergence, there is the development of some ideology, which means seeking on a predefined opinion, on a predefined convincement, which doesn't allow the opposite interpretation, diverse interpretation. And I think it is something to be avoided. Okay. And you may think that this reasoning that I am making is irrelevant. Actually, when you talk about models of the Earth system and uncertainty of these models, these reasonings are extremely relevant to consider the opinion of the minorities, to make sure that there is diversity, to stick on ethics, etc. Okay, now, let me go back to the web page because I want to make sure that I'm not forgetting anything. So mathematical model, box, deterministic versus stochastic, I think it's okay. Uncertainty assessment, okay. State of the Earth system and perturbation, okay. I mentioned the importance of describing the state of the system that we want to describe. In this case, it's the Earth system. And it's important to describe it because the state determines the output variables, determines the climate, determines our decisions. And actually, it is also important because the state of the Earth system is continuously changing. So we usually live under the perception that it's stable, but it's stable because the span of our life it's very short compared to the time scale of the Earth system. If we had the opportunity to live, I don't think it would be an opportunity, but if we had the opportunity to live for 1,000 years, we would realize that the Earth system is not stable. And it's continuously exposed to natural and human-induced perturbations. And therefore, the state is continuously changing. And if we want to describe the effect of climate change, and in order to set up adaptation policies, we need also to understand these perturbations, including those that are natural. And there are several examples of natural perturbation. Let me see if the next slide gives the examples. Just 1 second. No, the examples are given here in the web page. So volcano eruptions, these are natural disturbances. Okay, this is a list of possible natural disturbances. Volcano eruptions can change the climate. They are infrequent, but not so infrequent actually. Asteroid impact, you know, it's something that fortunately occurs on a time scale that is very long. And so we don't realize asteroid impacts. And 1 second, because see that there is something in the chat. 1 second. Yeah. So in the chat, I read that the audio sometimes doesn't work well. Is this? Yeah, I see 7 people. The problem is I can turn off the camera, but the problem is that I don't understand why. Usually it doesn't happen. Let me just make an attempt. Leave the camera off. Let me make another attempt. 1 second. Okay, I try to change the Wi-Fi, and I might lose the connection for a while. Hopefully not. If I lose the connection for a small while, just wait for me, okay? Let's try 1 second because it's not able. Okay, let's see. Changing now. Okay, now I change the connection. Let's see if it is better. And I can also, for sure, I can turn off the camera. And okay. Okay, just let me know if things improved. I'm sorry, I switched after 10 minutes. So let's see if it's better, okay? Just if you can write on the chat if you realize it's improved. I was talking about asteroid impacts, and can you please just send on the chat a message if now it's fine, one of you or more than one, it's not a problem, so I can see it. So I was talking about asteroid impact. As I said, it's something that occurs on a very long time scale, so we don't realize the potential, but actually the asteroid impact occurs continuously, and it has the potential to induce big changes. Okay, slightly better, hopefully. It has the potential to induce big changes in the Earth system. And I want to give you an example. If you look at the shape of the Earth, you can recognize a small number of craters originated by asteroid impact, and they look like a few. And if they look like a few, is that we have the atmosphere rainfall continuously shaping the Earth's crust. And therefore, we cannot recognize all of them, all the impacts that the Earth suffered in its long history. If we look to a planet without atmosphere, without movement of water, without rainfall, like Mars, craters, billions of craters, which basically are due to the impact of asteroids in the course of billions of years. And these craters, once they are created, they remain there. And one of the possibilities, one of the hypotheses that are considered for the disappear of water on Mars, we know that on Mars there was water and now there is no water anymore. One of the hypotheses is that Mars was exposed to the impact of a huge asteroid, which changed the inclination of its axis, changed the climate, and provoked a cascade of effects that determined the atmosphere of Mars to disappear and then the water to disappear. So these perturbations are indeed important, and as I said, the time scale is very long, and they have the potential to destroy the planet, by the way. Earthquake may induce the release of dust, debris, and toxic gases, the cooling of the Earth's nucleus. This is another thing that is I mean, it's we know for sure. It's in a way strange to realize. We know for sure that the Earth nucleus is going to cool down, and the cooling of the Earth nucleus may the annihilation of the magnetic field, which may disappear. And if the magnetic field disappear, it would be a big problem because it's the magnetic screen. If the magnetic field is a screen against the sun rays, the dangerous sun rays, and they are in a way reflected by the magnetic field. The most dangerous sun rays are reflected by the magnetic field. So we know that cooling of the Earth's nucleus in the long term will cause this effect, and to the dangerous sun rays with the end of life over the planet. Also, is another interesting phenomenon. It's a change in the planet's magnetic field such that the position of the poles is inverted, and so this north and south pole are switched. And the Earth field has alternated between periods of normal polarity, in which the dominant direction was the same as in the present time, and reverse polarity, which it was the opposite. And this period called Crohn's, and there is a lot of research activity aiming to predict what the evolution, aiming at predicting when the next switch will occur. So these are some examples of induced perturbations are deforestation, viral pandemic, and climate change, for instance. And note that I wrote these notes before the pandemics, because I was told by a famous virologist that in 2019, actually, she said, I am concerned by the possible onset of a global pandemic. And it is a risk that virologists knew quite well. Okay, and then we study then these different phases of the Earth system through Earth system sciences. And what we aim to do is to give a shape to these mathematical models. And we will discuss during the next lectures what kind of shape we can give to these models, what kind of equations we can use. I think this is an interesting discussion, because it brings us to gain a first knowledge of the tools that we may use for predictions. Okay, now I would like to switch to introducing the software that we will use for our practical exercises. Before doing that, do you have any questions? And do you have any other comment on the quality of the audio? Hopefully, I think it will be recorded fine. So if you missed some chunks, I think the recording may be clear. So you may refer to it. Do you have any questions? Okay, so let's now, we have 25 minutes. Let's introduce the software that we will use for our practical exercises. It's not the only one, okay? So let me go to Google. Let me close this presentation. So I try to clear my PC, just 1 second. Okay, good, perfect. And let me close also this one. Okay, Google. So let's search for R project. And it's better if you put a minus here, minus sign between R and project. It's not necessary. Anyway, if you just Google for R project, the first link that you get is this one, the R project for statistical computing. And as I mentioned to you last time, so we can click here. And there are several links in this page. It is a basic page. It's not fancy. And let me check. I want to make an attempt to turn my camera on because I think if you see my faces, it's better. If the quality of the audio goes down, just let me know, okay? It's not a fancy web page because when you get into the domain of public softwares, open softwares, you know, the look it's given low priority. And these are softwares developed by a free community. It's a community of people that are not paid. So of course they have to optimize their resources. One first set of link that is interesting to you is the documentation, and in particular the manuals. Let's try to explore this page. Here you see that there are several links, and what is interesting to you is the first one, an introduction to R. This introduction is easy to read. You don't need to read it. You don't need because we will work together, and I will tell you the information that you need. And on the other hand, if you wanted to, in a way, to improve your knowledge of the software, here the introduction to R is a useful reference. If you click on the PDF, you get this manual, and it's 100 pages. You may say too many. Actually, they are not too many because it's a manual, and you don't have to read all the sections in sequence. You just need to read what you need. And so it can be a useful reference. As I said, you are not required to read it. Okay, let's go back to the download page. And as I mentioned to you on Monday, if you write here, then there are several mirrors. You can get whatever mirror you want. And let's wait for it. And here you get to the download for Linux, Mac, and Windows. And most of you are Windows users. So if you go here, download R for Windows, you have to download the base, okay? And indeed, there is written here, this is what you want to install R for the first time. So if you download this, it's an installer, okay? And you just need to double click on it, on the file. Let me download it. And now I'm stopping the download because it's too long. I have already it in my PC. And then if you double click on the installer, you get it installed. Take all the default choices. The installer, as usual, asks you several options. take the default. Okay, you don't need to select different options. And then you get your R installed, and you will get an icon on the desktop. You double click on the icon and it will start. What you get is something that now I will show you, similar to what I'm getting. Similar but not the same, because I am working in Linux, and therefore I get an output that is, I get a look of the program that is different from what you get. There are some differences. You may wonder why I am using Linux and not Windows. Okay, this is an interesting question. There are several operating systems that you can select for your PC, and the operating system is an interpreter. It is an interpreter that between you and the machine, and the interpreter is in charge of getting the information from you, from the keyboard, from the mouse, and translating this information in something that the machine can understand. And there are several options, and the reason why there are several options is that at the beginning, at the onset of the computer era, there were different approaches available because they had different requirements. So people developed, for instance, people working heavily in mathematics, they developed their own interpreter, which was very good, very efficient in making mathematical computations. Other people were interested in producing pictures, producing artwork, and therefore they developed their interpreter, which was particularly efficient in dealing with artwork. And other people wanted to make money from it, and therefore they produced an interpreter, an operating system that is particularly easy to use, because they wanted to sell it to the people that were not expert, who are the majority. And this is why you have now three main options. And so I think you know the difference between Mac and Windows. And even today, there are relevant differences in these three possible solutions. Mac is quite close to Linux. The difference is that Linux is free and Mac is commercial. You have to pay for it. And between Linux, Mac, and Windows, there are differences in terms of stress that is imposed on the PC, because to give less stress to the user, Windows is more user-friendly, so it gives less stress to you. Part of the stress is transferred to the PC, which means that the machine is overloaded. So I don't want to make I want to make a long story short, but even in this case, it would be very nice if you were able, and you put in your CV that you can use several different operating systems. I selected Linux because for what I have to do is more efficient, and the less stress on the machine is a little bit more difficult to use, but it's also more efficient in terms of computational time. It's less exposed to viruses. Now, today, we have good antiviruses even for Windows, but Windows is more exposed, and therefore the antivirus takes more resources from the machine, another overload. So I selected Linux for this reason. And some people select Linux because it's free, and it's not a matter of money. You don't pay much for Windows, but it's a matter of concept. And so I think it is, the moral of the story for you is that the more you know, the better it is. Of course, you can't know everything, but if you see in your future a career that is mainly based on the use, the best use of the PC, I would suggest you to make an attempt also to install Linux. It can run even on an old machine. It's very easy to install and use. And after that, you know how to use Linux. Okay, so let me start in Linux. Once I clarified the why my screen looks different from yours, let me start in Linux R. So you should be able in your PC to double click on it and start it. So let me start it. So what you get in your PC, let me just make this bigger. Okay, what you get in your PC, it is something that it's similar to this. Okay, and 1 second, Q. Let me start it again because I made a mistake. Okay, perfect. So something that should look similar to this introduction here. Our version, your version is different from mine, and etc. But you should, now it's in Italian here. I think you selected English as your language. And so you get to this console. What is the console? The console is a window that is waiting for your input. If you are a Windows user, you get also menus in the upper part of the console. So now let me clear the screen, and the way to clear the screen is Control L, and you clear the screen. Let me take a larger font. 1 second. Okay, here it is. Okay, now I have a larger font. So as I said, I cleared the screen. You get menus up there. So what is the purpose of menus? You know better than me. The purpose of menus is to provide you some quick options, some quick commands, and in a user-friendly way. Meaning that, for instance, if you want to save, you have a menu with a save option, etc. And menus have the purpose of facilitating your interaction with the PC. On the other hand, menus reduce the flexibility, your flexibility, because they give you only a restricted number of options. This happens also in Word and Excel. You have several more menus than here in R, but still the number of options is relatively small with respect to what Word and Excel may offer. So the purpose of menu is to make the interaction with the user easier. On the other hand, they are not very flexible. So this is the counterpart of them. Now, why this software R is not as user-friendly as Excel? This is an interesting question. Excel is conceived, like Office in general, to be very user-friendly. And so it is a software that is called what you see, what you get, meaning that in Excel, you can introduce data and you can see everything. After you have introduced a number in a cell, you see the number. And clearly you have continuously a vision of what is the information that you are plugging into Excel. On the other hand, this user friendliness is paid back in terms of flexibility, as I said, and in terms of the efficiency of the machine, because a lot of resources are dedicated to the interaction between you and the machine. The developer of a more sophisticated software, usually has another priority. The other priority is to optimize the performances, and therefore, in this case, by using resources that are not paid, because these free public domain softwares are developed, as I said, by communities that don't get any money from them. So they have to optimize these resources, and therefore the user friendliness is lower. So you are required to be more skilled in order to use MATLAB, to use R, because they take the commands mainly from the console. The console is what you can see on the screen. Now you need to know an instruction. You don't have a menu for doing everything here. You need to know the commands. On the other hand, because these softwares are more complicated, they are used by a more restricted number of people. It means that if you develop good skills in using software that is more sophisticated, these skills become one of your distinguishing skills. So, I mean, the reason why I am inviting you to use software that is less user-friendly and, on the other hand, more efficient is that I want to indicate to you ways to improve your CV, to improve your skills. A few words on the difference between public domain software, open source, and commercial software. In this case, even if we refer to two softwares like R and MATLAB, which are more or less difficult to use at the same level, R is public domain open source. MATLAB is commercial. They have some differences also in terms of toolbox available. So some things, some tasks are better done in MATLAB, other ones are better done in R. So they have some differences, but the basic difference between the two, the striking difference, is that MATLAB is commercial and R is public domain. Even if MATLAB is not so expensive, still some of the toolboxes are not very cheap. There is a big difference between a commercial software and a public software, because the commercial software you need the license. Now you can use it because you are a student at the University of Bologna, so we have a campus license. But once that you are no more a student at the University of Bologna, you cannot use MATLAB, and some of the toolbox cost like 1,000 euros. So I think it is an advantage to be able to use to make the same task with an open source software. And there is another difference. The open source software is supported by an open source community, which means that you don't have to pay for assistance. You can get assistance more easily, and you can get also pre-prepared softwares more easily. So the moral of the story is that it's very good if you can use MATLAB, but it's also an added value, a significant added value, if besides MATLAB you can use a software like R. Okay, perfect. Now let's start with R. We have 10 minutes, less than that. So R is waiting for your input. Let's start with the easiest thing to do, a basic operation. 2 plus 2, return, you get 4. Sorry, yeah, 4. I couldn't see it because I had the mouse over it, so I was a bit puzzled. Okay, and you can also make other operations, also in sequence. 2 times 3 plus 4, it's 10. Be careful of the priorities. So what I've written down, it's the same as parentheses 2 times 3 close parenthesis plus 4. Okay, I get a different results if I make 2 plus 3, 2 times 3 plus 4. Here I get 14. So you can use parentheses, everything, and you can also make more, of course, more complicated computations. And another computation, sorry, you can use also pre-prepared computation. So for instance, if you need to compute the square root, the square root can be computed in this way. 16, for instance, at the power of 0.5, good. And you see the hat for the power. But you can also compute the square root by using a function, because R has embedded some pre-prepared computations, which are called functions. And the name, but to use the function, you need to know their names. So what is the name for the function square root is sqrt. And if I want to compute the square root of 16, I can use this function sqrt. And I have to give the argument between round parentheses. So sqrt of 16 is 4. Now the question is, how can I know the name of the function? So first, let me clear the screen, Control L. Let me say that if you knew the name of the function, you can get additional help on the function with the use of the question mark followed by the name of the function. And you get an help. Windows users, you will get an help through a web page. So it will open the browser and it will give you the help. And you see that there is a lot of information on these functions, sqrt, ABS. But what if you don't know the name of the function? Okay, very good question. Let's open a Google page, Google, and let's search for square root project. This is the easiest way to get help into R. And you see that there is take the first link, no matter what it is, and you get here, square root. You get the name of the function. Okay, and 1 second. Okay. Now here the example doesn't compute the square root of the number. It computes the square root of a variable that I defined. How can I define a variable? Let me go back to the console. In this case, I can write sqrt x. Let's suppose that x is a vector. In order to define a vector, I have to give the elements between parentheses, but I have also to use a function which is called c. So 1, 2, 3. This is a vector. Now, if I type x, I get the vector, and if I type sqrt x, I get a vector with 3 numbers, which are the square roots of each element of the vector x. So I already defined variables and vectors. Okay. Now, I don't want to move much forward. My invitation to you is try to play a little bit with R, making simple computations, try to repeat computations, simple computations that you have done in Excel. And you may use additional functions like logarithm, like whatever. Okay, sin and cos, trigonometric functions, and you don't know the names, no problem. And of course, sin pi, where pi is pi, and you see that it's 0. Okay, and cos pi. So the best way to learn a new software is through trial and error. The quickest way, it's not the best way. If an informatic listen to me saying this, they will kill me. But I think the quickest way to learn a software is starting with playing with it. Okay, so try to start playing with the software, and then next week we will work together again. And if you have any problem with this, contact me. Okay, send me a message, an email, or we may set up for some of you, a group of you, an additional half an hour of group conversation, even virtually. It doesn't require that you move from where you are. No problem. I am at your disposal. Okay, and just try to start playing. Do you have any question? I hope that the audio was running fine after 10 o'clock, 10:10. In any case, I will upload the video soon, and I hope that everything is working fine. No questions? Let me just de-share the screen and stop the recording.